Afternoon, students. Today we will think about factor analysis. Lecture goals. In this lecture, we would like to understand the definition of factor analysis. In order to do that, we would like to understand the explanatory factor analysis and confirmatory factor analysis. Also, our goal is to understand the principal component analysis and common factor analysis. We would like to probably principal component analysis. Finally, we would like to use SPSS for the factor analysis. Part 1. Understanding factor analysis. First of all, we need to understand what is factor analysis. Basically, factor analysis is a statistical method used to describe variability among observed correlated variables into a potentially lower number of unobserved variables called factors. So as you can see, there are three observed variables. They are normally called indicators. So multiple indicators are involved in that. So using those multiple number of observed variables, we would like to have unobserved factor, or sometimes called latent variables. In other words, it is possible, for example, that variations in 3 or 4 observed variables mainly reflect the variations in fewer unobserved variables. So, factor analysis searches for joint variables in response to observed indicator variables. The unobserved variables, sometimes called prominent component, are modeled as linear combinations of observed variables xij plus error terms. So as you can see, we have now 3 observed variables x1, x2, x3. Utilizing those information, we are gonna select latent, sometimes called unobserved principal components. The information gained about the interdependencies among observed variables can be used later to reduce the set of variables in a dataset. Computationally, this technique is equivalent to lower rank approximation of the matrix of observed variables xij. So, we can think that factor analysis originated in psychometrics and is used in behavioral sciences, social sciences, marketing, product management, operations research, and other applied sciences that deal with large quantities of data. So more specifically, we would like to investigate what is the nature of explanatory factor analysis. Explanatory factor analysis, in short called EFA, is used to identify interrelationships among items and group items that are part of unified concepts. The researcher makes no a priori assumptions about interrelationships and the relationship among items and factors. This is the picture representing the nature of explanatory factor analysis. In the first stage, we are given observed indicators. In this example, we have now 9 observed indicators. Those are indicators also called observed variables, measured basically based on the questionnaires. So among those 9 variables, we would like to see the factors, unobserved latent variables. In this example, 3 unobserved latent variables are extracted out of the information from 9 observed variables. So, I'm ready to explain about principal component analysis. Principal component analysis, in short, PCA, is a widely used method for factor extraction, which is the first phase of EFA. Factor weights are computed in order to extract the maximum possible joint variance. The keyword is joint variance, with successive factoring continuing until there is no further meaningful joint variance left. The factor model must then be rotated for enhancing group efficiency of factorization in the analysis. So, exploratory factor analysis, EFA, is related to principal component analysis, PCA, but the two models are not basically identical. Latent variable models, sometimes called structural equations modeling, includes factor analysis, also use regression modeling techniques to test hypotheses, producing error terms, while principal component analysis, in short PCA, is a descriptive statistical technique. So, as I have already mentioned in the previous stage, there are 3 observed variables, x1, x2, x3. Out of those information, we would like to extract unobserved principal components. They are sometimes called latent variables. They are sometimes called factors. In this process, Wij, representing 9 weight variables, including W11, W21, W31, up to W33, is called factor weight. Sometimes it is called factor loadings. So, in a graphical demonstration, we would like to define the principal component analysis as follows. As you can see, there are 3 observed measured variables, x1, x2, x3, and those 3 observed variables is now producing 3 unobserved latent variables, PC1, PC2, and PC3. Those latent variables is characterized as unobservable variables, and those variables representing the joint variation belonging to the observed multiple indicators, in this example x1, x2, x3. And Wij represents the factor weight, sometimes called factor loadings, representing the relationship or association among multiple observed variables and selected or extracted unobserved principal components. There has been significant controversy in the field over the equivalence between the exploratory factor analysis and principal component analysis. So I understand that principal component analysis is a part of exploratory factor analysis. Principal component analysis is the most commonly used methodology for pursuing exploratory factor analysis. It is the most stable method for exploratory factor analysis. Now we are ready to move on for understanding confirmatory factor analysis, CFA. The confirmatory factor analysis is a more complex approach that tests the hypothesis that the observed items are associated with unobserved specific factors. Confirmatory factor analysis uses structural equations modeling to test a measurement model whereby loadings on the factors allows for evaluation of relationships between observed variables and unobserved variables. Hence, it is efficiently used for the measurement part of the structural equations modeling. So component factor analysis can be illustrated in one picture or figure. In this example, we have 9 observed variables called indicators. Out of those 9 observed variables, we are now extracting 3 unobserved factors. Also, we understand those 3 factors are associated with 3 corresponding observed indicators respectively. So we would like to measure the factor loadings represented in green, represented in pink, represented in yellow. That is the basic nature of confirmatory factor analysis. In this example, we are now using 5 observed indicators, including family income, father's education and mother's education, language scores, and math scores. Out of those 5 variables, we are now extracted 2 latent variables, socioeconomic status and academic scores. Of course, those 2 factors are not observed, so they are latent variables. So in the confirmatory factor analysis, we will check the size of the association. In this example, 5 factor loadings is now existing, so we can estimate the size of the statistical association corresponding to those 5 factor loadings. And then we can perform the factor regressions running from socioeconomic status up to the academic scores. So normally the confirmatory factor analysis takes this form. This is the observatory part belonging to the structural equations modeling. So in this example, we have now 1, 2, 3, 4, 5, 6, 7, 8 factor loadings. Out of the confirmatory factor analysis demonstrated in this figure, we can estimate those 8 factor loadings as a result of the confirmatory factor analysis in green. Now, let me summarize the specific concept or the definition of terminologies normally used in factor analysis. The factor loadings. Number 1. The factor loadings, also called component loadings in principal component analysis, in short PCA, are the correlation coefficients between the observed variables. Those are indicators located in rows, and unobserved factors represented in columns. Analogous to Pearson's R-squared, the squared factor loading is the percent of variance in the indicator variable explained by specific factors. So, how many factor loadings? we have now 9 times 3. In total, 27 factor loadings has been estimated and reported in this factor loadings table. As we have already understood in the previous page, the factor loadings represent the statistical association among the observed variables starting from V1 to V9 and unobserved extracted factors starting from 1 to 3. So in total, 27 factor loadings has been estimated and reported in this table. Another interesting thing is the square of each factor loadings represent the Pearson's R square, explaining the explanatory power by the factor by each factors about the variation in the variables. So eigenvalue will be defined as vertical summation of squared factor loadings. In this example, the first principal component extracted explain how much 2.436 variation of variables. That is the summation of all squared factor loadings in column wise. That is the meaning of eigenvalue. Another meaning of interesting concept is communality. That is the horizontal sum of squared factor loadings. So the first variable denoted as V1 explain the variation in all three components variables 1, 2, 3. How much? 0.474. That is the summated squared factor loadings 0.418 square plus 0.543 square plus 0.069 squares. So let's try to interpret factor loadings. By one rule of thumb in confirmatory factor analysis, factor loadings should be 0.7 or higher to confirm that independent variables identified a priori are represented by a particular factor on the rationale that the 0.7 level corresponds to about half of the variance in the indicator being explained by the factor, because the squared value of 0.7 is equal to 0.49. This is almost the half of the variance in the indicator being explained by the factor. However, the 0.7 standard is a high one, and real-life data may well not meet this criterion, which is why some researchers, particularly for explanatory purposes, will use a lower level such as 0.4 for the central factor and 0.25 for other factors, called loadings above 0.6 high, and those below 0.4 low. So as you can understand easily through this paragraph, the normal standard is the cutoff is 0.7. However, some researchers require the value of factor loadings above 0.6 as high and below 0.4 as low. In any event, factor loadings must be interpreted in the light of a theory, not by arbitrary cutoff levels. Now, number 2, eigenvalues. The eigenvalue for a given factor measures the variance in all the variables, which is accounted for by a specific factor. If a factor has a low eigenvalue, then it is contributing little to the explanation of variances in the variables and may be ignored as redundant with more important factors. So in summary, eigenvalues measure the amount of variation in the total sample variables under study, which will be accounted for by each factor. Number 3, percent variance. To get the percent of variance, normally denoted as percent variance in all the variables accounted for by each factor and the sum of the squared factor loading for the factor column wise, and then divide by the number of indicators. So it's defined as eigenvalue measured divided by the number of indicator variables. This is the same as dividing the factor's eigenvalue by the number of variables. So in summary, eigenvalue is the sum of squared factor loadings. So in the first stage, eigenvalue, which will be measured in column-wise summation of squared factor loadings. Stage 2, the estimated eigenvalue will be divided by the number of variables under study in the sample. So percent variance is the eigenvalue divided by the number of indicator variables measured, observed. Number 4, communality. What is communality? Communality is the sum of the squared factor loadings for all factors for a given indicator variable. It is the variance in that variable accounted for by all the factors, and this is called the communality. It's the horizontal summation of squared factor loadings. The communality measures the percent of variance in a given variable, which will be explained by all the factors jointly and may be interpreted as the reliability of the indicator. So if you have a high communality, it represents the variable used as indicator is very reliable. Next, number 5, factor score. Factor scores are the scores of each case on each factor. To compute the factor score for a given case, for a given factor, one takes the case's standardized score on each variable and then multiplies by the corresponding factor loadings of the variable for the given factor and sums these factors. So computing factor scores allows one to look for factor outliers. Also, factor scores may be used as variables in subsequent modeling. In this table of factor loadings, we have 3 factors selected or extracted from the given information of 9 indicators. Of course, those 9 indicators will be observed indicators. So those 9 observed indicators will produce 3 principal component factors. Column-wise, we can summate the squared factor loadings. For the first extracted factor, we have eigenvalues equal to 2.436. That will be measured by the summated squared corresponding column-wise factor loadings. How would you then to calculate the eigenvalue of the second principal component factors? In order to do that, you will summate all squared factor loadings corresponding to the second factors column-wise, and then you will get the eigenvalues. Also, in the same way, we can calculate the eigenvalue of the third extracted factors. Okay, that's the eigenvalues. Column-wise summation of squared factor loadings. Alright. Second, communality. How would you get the communality? In order to get the communalities, then you have to summate all squared factor loadings horizontally as opposed to vertically. So horizontal summation of squared factor loadings will give you the communality for each observed indicators. In this example, for the first observed indicators, communality is 0.474, which is obtained by summation of squared factor loadings horizontally. The higher the communality, the more reliable the selected or observed indicators. Rotation, that's number 6. The factor model must then be rotated to enhance grouping efficiency of factorization in the analysis. In this process, most of scholars use Varimax rotation. The Varimax rotation is most widely and frequently used as the method for reducing the number of columns, which is factors. It is basically a technique for reducing the number of columns. Why rotation? Because in the before stage, factors, the factors and the coordinates are not very clear to identify whether the first variable belongs to the first factor or second factor, because its factor loadings is very mediocre. It's in the middle between 0.2 and 0.4. Most of all values are located between 0.2 and 0.5. It's very middle. So we cannot, clarify which variable belongs to which factor. I don't know. So we can rotate the situation to the second stage of the after rotation case of the S6, and the coordinates will change a little bit, 0.3 to 0.6, 0.45 to 0.1, something like that. So we have a case of after the location of S6. We can polarize and we can clarify which variable belongs to which factor. In this example, indicator x1, x2 has a relatively high factor loadings to the first factor. So x1 and x2 belongs to the first factor, and x3 belongs to the second factor, because for the second factor it has relatively high value of factor loadings. The rotation has two cases. First, orthogonal rotation. Second, non-orthogonal rotation. In the first case, orthogonal rotation keeping the angle of the x-axis and y-axis as orthogonal. In the second case, the angle between the s-axis and y-axis is allowed to be less than 90%, which is called the case of non-orthogonal. Okay, now we are ready to practice using SPSS. So, in order to do that, I ask you to install SPSS software in your personal computer. I uploaded SPSS software in iCampus. Why don't you download? Why don't you unzip? Why don't you install SPSS by clicking twice the exe file there, and then you will bring the practice data. The practice data here is factor analysis, mobile banking, KLSB, global MPA, and factor named. I've already uploaded that specific data for practice in the iCampus. So I successfully brought the data, and I go to analyze and data reduction and factor analysis. Okay, in this case, analyze, data reduction, and factor analysis. And then we are now supposed to move the corresponding variables to the right, and description. You can click description, and then coefficient and KMO Bartlett test of sphericity, and then continue, please. For the extraction, we can check the script plot and eigenvalues. For the rotation, Varimax and rotational solutions, and then continue. And then scores, save as variables, regression, and display factor score, coefficient method, matrix, continue. And then options, exclude case pairwise, sort it by size, and then continues. You can get the KMO Bartlett. If you have higher than 0.5, then your data can be suitable for the factor analysis. Eigenvalues and percent of actually this is a rotation sum of squared loadings, total percent of variance, and communality percent. And then the percent of variance will be obtained by dividing eigenvalue by the number of variables. How many number of variables? 24. Eigenvalue. What is the value for eigenvalue? 3.415. And then script plot. The cutoff of eigenvalue should be 1. At least one variable will be explained by a selected factors. That is the requirement in this case. And then script plot will show me how many? 7 factors is okay, satisfying the cutoff value of the eigenvalues. This is the table for factor loadings. So my recommendation is to use rotated component matrix. Component score coefficient matrix will be used to select the factor scores. So we can have a factor score on the spreadsheet. If you check it, you can find this. Finally, Cronbach's alpha. Please go to analysis, scale, and reliability analysis, and then check it with alpha. That's the button for the Cronbach's alpha, and then specify for each factor with observed variables. Analysis, scale, reliability, analysis, and then alpha. So as you can see from the exploratory factor analysis, we know that the first factor will be explained by 4 variables: x13, 14, 12, and 15. The second factor will be explained by how many? 6 variables. x3, x2, x24, x23, x23, and x1. Those factor loadings should be higher than or equal to 0.5. The third factor will be explained by how many? 5 corresponding variables. x18, 19, 20, 21, 5, and something like that. After that, we can finish groupings, and then we can name. For example, the first factor, as we have already discussed, 13, 14, 12, 15, here 12, 13, 14, 15 will be the first factor extracted from the designated 4 variables, 12 to up to 15. So as a researcher, I will name that as security. The second factor will be named by myself, customer. The third factor will be named by marketing, something like that. So let me ask you, who will name the factors? The answer, researchers. So named factors will appear on the spreadsheet. Okay, so you can naming in the variable section, and then you can regression, and then you can use the factors extracted. You can use the factors extracted and then perform regression analysis. The dependent variable y and independent variable 6 independent, actually 1, 2, 3, 4, 5, 7 independent variables, and then we can get the results from the table. Unstandardized and standardized coefficients, and then significant. All factors extracted from the indicators are statistically significant associated with the dependent variable y. Y is the satisfaction of a mobile service. So homework 7, I uploaded assignment 7. So you can use the separately provided data in the iCampus assignment 7. Why don't you complete the requested questions? Thank you, students. I'd like to wrap up the lecture about factor analysis. I hope to see you next week with structural equations modeling by using Amos next week. Thank you very much. Please enjoy the evening. I hope to see you in Korea soon. Thank you very much.